So, we were seeing this steady vaporization problem, and the mass evaporation rate per unit area, which is mass flux. So, you can say rho A VA, mass of the fuel, is expressed in terms of the mass transfer basis as well as the heat transfer basis. See, the mass transfer basis, it is rho dAB by L, natural logarithm of 1 plus By, which is the Spalding transfer number given as YAI, that is the liquid A is evaporating. At the interface, what is the mass fraction of the A, the gas phase, that is YAI, and at the far field x equal to L, the mass fraction of A is YA infinity divided by 1 minus YAI. So, that is the definition of the By, which is the mass transfer based Spalding transfer number. Then, by solving the heat transfer equation, this expression is got kg by Cpl, natural logarithm of 1 plus Bq. Here Bq is defined as Cp into T infinity minus Ts divided by hfg. So, in the steady evaporation, there is a clean coupling between the heat transfer and the mass transfer, and the heat coming from the gas phase is given to the interface, and that is used for vaporizing the fuel. So, the liquid phase heating is not present. So, that means we can equate these two, the mass transfer based expression as well as the heat transfer based expression. So, you get this 1 plus By equal to 1 plus Bq power Le, where Le is the Lewis number, kg by rho dAB Cp. So, Le equal to kg divided by rho Cp dAB. So, nothing, k by rho Cp is alpha, so it is alpha by d. So, that is the Lewis number. So, you can see this is the expression we have got. If Lewis number equal to 1, then we will have By equal to Bq. But generally we can handle non-unity Lewis number also using this expression. So, now when I equate this, when I write this in a expanded form, I get this equation C, where the interface mass fraction in the gas phase of the vapor A will be equal to 1 minus YA infinity divided by 1 plus Bq, this is Bq power Le. So, this is the expression I have got. Now, how to find the value of YAI? For that, I need to know the value of Ts. So, T infinity is known, YA infinity also is known, and the properties Cp, hfg are known. Lewis number can also be calculated. So, T infinity, based upon the value of T infinity, there will be some value for Ts because of the heat transfer that is coming in from the gas phase to the interface. Based upon the value of Ts, there will be a certain value for YAI. So, how to calculate that? So, YAI is a function of Ts. It is evaluated by solving the equation C. But to connect Ts and YAI, I need a thermodynamic relation. Thermodynamic relation such as Clausius-Clapeyron equation. We also have another equation called Wagner's equation, etc., which actually gives the relationship between the temperature, this is temperature of the surface, and the corresponding saturation pressure for the temperature. So, in the thermodynamic equilibrium condition, the saturation pressure at the given pressure, saturation temperature at the given pressure, the saturation temperature at the given pressure will be fixed, or we can say at the saturation pressure at the given temperature is also fixed. So, when I say T equal to Ts, then corresponding Psat can be taken as the vapor pressure Pv. So, that is a liquid, and there is some vapor over the liquid surface. This is interface, there is some vapor over the interface. So, this vapor imparts some pressure, say PV, which is equal to the saturation pressure at the given surface temperature. So, that is the expression for which you need to use the HFG. This is the specific gas constant of the fuel, and this is the boiling point of the fuel. So, using that you can do this. So, now you can note that if Ts, this is surface temperature, tends to T boil, then XAI will be equal to 1. Okay. So, the factors affecting T infinity tending to infinity or HFG tending to 0 will make YAI to tend to 1. So, T infinity tending to infinity means it is more than the boiling point. So, if Ts approaches boiling point, then XA approaches 1, so that YA also will approach 1. So, how to calculate this equilibrium condition? This is the procedure to calculate the interface quantities. So, first of all, T infinity is fixed for a given T infinity. So, now I assume a value of Ts, then use the Clausius-Clapeyron equation, which is the equation D, and calculate P sat at Ts. That is what I am doing here. Then P sat equal to PV, the vapor pressure, which is equal to, so this ratio will be equal to mole fraction of the fuel at the interface, from which I can calculate the mass fraction. So, mole fraction and mole fraction, mass fraction, mole fraction and the mass fraction YAI are related using molecular weight of A or the mixture, molecular weight of mixture. Then, since you know YAI, I can calculate BY. Similarly, if you know, since you know we have taken the value of Ts and T infinity is known, calculate BQ and see whether the equation C is satisfied, that is this equation is satisfied. If it is not, then the value of Ts has to be adjusted and the procedure has to be repeated to get the correct value of Ts, that is the equilibrium temperature. Now, T infinity is fixed. If T infinity is less than T boiling point, then Ts would approach T infinity. If T infinity is greater than boiling point, then Ts will approach T boiling point. That means Ts in the first case will be slightly lesser than the T infinity. Ts in the second case will be slightly lesser than the boiling point. So, this is evaporation and this will be combustion. When combustion occurs, the flame is around over the fuel surface. So, the T infinity is much higher than the boiling point. So, this is how you calculate the interface quantities. Now, when you do this, graphically we can represent this. So, what I vary is T infinity. Okay, now XF, see here F is nothing but A, fuel. So, you can say X, this we can say, or Y A equal to YF. Okay, just A and F is interchanged here. So, now we can see that this dark line shows the relationship between the mass fraction and the surface temperature Ts. So, this is YF. Okay, now when Ts surface temperature approaches the boiling point, then YF will approach 1, or else it varies like in a very non-linear form. Now, this is the thermodynamic equation. This dark line is nothing but the equation D. Now, we can get the intersections of these curves. What are these curves? These curves are nothing but by solving the equation C. So, these intersections of these curves, see for example this is low T infinity and T infinity increases and it is increasing like this. Now what is the surface temperature Ts for this given T infinity? So for example say this is T infinity 1, 2, 3, 4, 5 and this is T infinity 6, then this is the surface temperature Ts6 I can say. So where the equation C intersects the equation D, that is the solution for the equilibrium temperature. So this is the way we solve for this. So when steady evaporation take place, okay, interface is here and this is x equal to L and here I say Ya infinity, Yai and this is Ya infinity, mass fractions of the liquid A here in vapor phase. The liquid A evaporates, the intersection has gas phase here and liquid phase here and Yai is the vapor phase mass fraction of A just above the interface and this what will be this value of Ts, corresponding value of Yai can be got and this Ts is dependent on the T infinity. So that is what this map shows. Okay. So in the case of equilibrium or steady evaporation, we have a definite value of the surface temperature Ts for given T infinity, which is got by balancing the thermodynamic equilibrium or thermodynamic relation between Ts and Psat or P vapor pressure and solving the equation relating Bq and By. Okay, now evaporation is seen. So evaporation, what are the factors controlling evaporation, etc. we have discussed. That is the ambient temperature, HFG, the volatility which is dictated by the boiling point, then latent vaporization, etc. So those affect the evaporization and that is the rate limiting step for the burning of a liquid fuel. Now how to ignite it? So let us first consider piloted ignition, that is ignition using an external source. So we can recall that we have done the cone calorimeter this where I can keep a liquid fuel sample and subject this to a heat flux using cone. So what happens is this the liquid gets heated up and some vapors are formed and air comes from the ambient and mixture is formed and this mixture can be ignited to get a flame. So we have seen that there is a critical heat flux as well as there is some given temperature for the surface which will cause the ignition. We have also seen that for a momentary ignition to be caused, Ts should be approximately equal to or slightly greater than T flash, the flash point temperature. For a diffusion flame to sustain, Ts should be more than the fire point. So this is flash. So for ignition, sufficient vapor should form over the liquid surface and ignition source is kept, then a momentary flame is formed. That means the liquid has to be heated to its flash point, if it is not at the flash point already. So for heating, see if there is a sub flash point liquid, for example the flash point is more than the ambient temperature, then from the ambient temperature which is the liquid's initial temperature, an external heat source should be used to heat this to the flash point where it will produce enough vapors. Then you can try to ignite it and further heat it to get to the fire point where a sustained diffusion flame will anchor. Now fuel with flash point lower than the ambient temperature like gasoline, N-heptane, methanol, etc. Since its flash point is lower than the ambient temperature, liquid will usually be in ambient temperature condition. So it is over, like the temperature is more than the flash point. So enough vapors will already be available adjacent to the surface of the fuel, and it can mix with the ambient air. In this case, I don't need any additional heat source. So that is why low flash point fuels are categorized as hazardous, class 1. Now, the reactant mixture, that is the vapors which are coming out of the interface and the air from the ambient, the reactant mixture formed over the liquid surface, then an ignition source will cause a momentary premix flame. Then we have to wait for some time to produce enough vapors and form the mixture again, and the ignition source will cause another momentary flash. That means here the flash point is the condition where ignition can be caused, but that may not sustain the combustion or formation of a flame completely. So that is the point we have to understand here. So flash is formed, then the vapor is consumed. Then we have to wait for some time to produce a premix vapor. For this, say this is the surface, some vapor has to be formed, and this some volume, critical volume should be there. So that is enough vapors which is flammable is formed. Then the ignition source will cause the burning of this vapor, creating a momentary flame. But this will not sustain a diffusion flame. So when the diffusion flame is sustained? When the fire point is reached. Okay. So for external ignition, we have to understand there are two conditions: sufficient volume of reactant mixture, that is fuel, vapor and air, should be available over the liquid surface, and this volume of fuel and fuel, vapor and air should be flammable. That is, the mixture should exist within the flammability limit defined for the given fuel. So it should not be more than the upper flammability limit or lower than the lower flammability limit. Then second condition to get the pilot ignition is sufficient energy, which is called minimum ignition energy, should be used. That is, the heat source or the ignition source, say spark, etc., should have sufficient energy called minimum ignition energy, and that amount of energy should be transferred to the mixture to cause the ignition. So these are the two conditions: presence of minimum volume of a flammable mixture, then the ignition source with sufficient or minimum ignition energy. These are the two criteria. Then one more criteria is the ignition location. So again, consider a beaker with the liquid fuel, and from the air from the ambient comes in and a mixture is formed. Okay, now if you go to the fuel surface, towards the fuel surface, you get more fuel rich mixture. If you go away from this surface, at certain point you will get air or oxygen rich mixture. These two may not be flammable. So that means if you locate your ignition source very close to the fuel surface, it will not ignite. If you take it very far from the fuel surface, then also it will not ignite. So there is a certain distance where the mixture will be flammable or within the flammability limits. In that location, you have to locate your ignition source. So the ignition location plays an important role. Ignition cannot occur too close to the fuel surface where fuel rich mixture, which may be more than the upper flammability limit, can exist. Similarly, it cannot be too far where the mixture can be lower than the lower flammability limit. So that means we have to follow some standard test procedure to determine the time for ignition, which is also called ignition delay, where the ignition is kept at a particular location from the fuel surface. Now, further you heat it, from the flash point you cause momentary flame to form, etc. Now, fuel surface or liquid has reached the fire point. Now what happens is, sufficient vapors are generated to sustain a diffusion flame over the surface. So here Ts is greater than T fire point. Now sufficient vapors are generated, to ignite it you get a diffusion flame formed over the surface. Diffusion flame is formed. Now, this diffusion flame basically will attract fuel from the surface, oxygen from the ambient air and sustain here. And this flame will also try to feed the heat back to the surface, so that the fuels evolve from the surface and feed the flame. So, a sustained flame is formed, which is non-premixed in nature. Flashpoint flame is a premixed flame, which is momentary. When the flash forms, then the ignition source has to be removed and we have to wait for some time to produce the mixture again. Then the ignition source should be reintroduced to form the premixed flash. Now, this is the diffusion flame. Once the diffusion flame is formed, we can remove the ignition source. The flame heat feedback itself will be able to produce more vapors to sustain itself. So, fire point, sufficient vapors, enough vapors are generated, and it will result in the formation of a flame, diffusion flame, and heat will be released. Now, this heat which is released, part of it will be lost to ambient, part of it will be fed back to this. So, if the heat released is more than the heat losses, which is the case here, that means some fraction, enough fraction of the heat from the flame is fed back to the interface, so that evaporation continues and fuel vapors are formed at the required rate and they feed the flame. Okay, now this flame can put off if there is a heat loss which is more than the heat which is released. So, main criteria is the heat released should be more than the heat which is lost to the ambient by radiation, by convection, etc. And sufficient heat feedback also should come to the surface. Now, if I take say crude oil, etc., we have talked about the crude oil spills in the ocean beds, sands, etc. Crude oil has a very high fire point. So, more than 200 degrees, something like that. Crude oil is a mixture of several oil and it is highly viscous also. So, now what should be done to ignite this? Basically, what we do is, if you just take a pilot flame, a propane flamer, and put it over a surface and heat it, it will not be ignited. So, basically what we do here is, you take a low flash point liquid, say like ethanol, methanol or N-heptane, etc. Okay, they are called prime fuel, and put it over the surface of the crude oil and ignite this. So, this, since it is low flash point liquid, it will catch fire easily, and the fire which is formed over the prime fuel. So, we have a situation here. So, there is a ocean, it is a water bed, water, and this is crude oil, and I put a prime fuel like gasoline, N-heptane, etc. Now, this burns because it is easy to ignite this. So, this burns. Then this will heat up this. When it burns, the flame will heat up this crude oil also more than its fire point. Then the crude oil will ignite. So, that is the way you have to ignite this. A normal spark or a flame will not be able to do this. We have to have one more layer of a low flash point liquid put over the crude oil and burn that, and that heat feedback should be given back to the crude oil surface, so that it heats up to the fire point and a sustained flame is formed over the crude oil. So, in the in situ burning we do this. Or one more technique is, put a wick material which is of low thermal conductivity, and you saturate that with some prime fuel and ignite it, so that heat is actually conducted back to the crude oil surface and it can burn. So, when you handle very tough liquids which cannot be ignited easily, you have to use low flash point like fuels, prime fuels, and burn it. So, ignition, piloted ignition is which is than using external ignition source. When you have the liquid temperature at flash point, you can cause a momentary premix flame formed over the liquid surface. There the criteria is there should be minimum volume of the flammable mixture formed, and you put the ignition source which has minimum ignition energy, and the ignition location also such that at that location a flammable mixture is available. Now, when you want to sustain a diffusion flame, the liquid has to be heated more than its fire point. Then you can sustain a diffusion flame, non-premix flame. For that, basically more heat transfer is required to increase the temperature from flash point to fire point. So once that is done, then no ignition source is required, external ignition source is required. The diffusion flame formed over the surface itself will be able to give the heat feedback to the liquid fuel and sustain the flame. Then when you have handle high fire point liquid like crude oil or any viscous oil, okay, then what happens is you have to put a low flash point liquid over its surface and burn it, or else ignition is not possible. So these are the factors affecting the ignition, the high fire point. So basically the volatility is very important. Then the temperatures like flash point, fire point are very important for ignition. Then let us talk about auto ignition. See, what happens in auto ignition is we don't need any external ignition source. The fuel vapor and the air mixture which is formed is actually exposed to a temperature which is called, is a high temperature which is called auto ignition temperature. Then this mixture ignites automatically. That means you can see that in the diffusion flame case, the fuel comes from the surface, oxidizer or the oxygen comes from the ambient air, and a stoichiometric mixture forms. But at that location, the temperature is high enough, more than the auto ignition temperature, so they burn immediately. So that means if you have a mixture which is flammable, obviously for the diffusion flame, the mixture is at stoichiometric proportions. So a flammable mixture is there, and the temperature of this this mixture comes into contact with the temperature which is more than the auto ignition temperature, then the mixture will be ignited without the need of any pilot flame or spark, that means any external ignition source. Okay, now you have a cooking oil which is kept and there is a flame from the bottom. This is heated, the cooking oil is heated. So vapors are formed and air from the ambient comes and the mixture is formed basically. Now what happens is, since the surface of the overheated cooking oil can be more than the auto ignition temperature, what happens is, or basically you can see that there will be some solid parts which will be having temperature more than the auto ignition temperature of the mixture, automatically a fire forms over the surface. So if you just leave the cooking oil without frying anything in the flames for long time, the oil surface will catch fire. That is basically due to the auto ignition. So that is one of the example. So in practice, a liquid fuel or a solvent which is flammable, when it comes into contact with the hot surface like machinery component etc., the surface temperature is very high, so that the vapor which is formed, that also comes out with a higher temperature and mixes with air. And if the mixture's temperature is more than the auto ignition temperature, then it can automatically ignite without the need of any external ignition source. So that is self ignition. The self ignition occurs when the vapor generated at a high temperature from the liquid and the mixture of this vapor, high temperature vapor and the air exceeds the auto ignition temperature, then there is no need for having any external ignition source. This is another thing. So, auto ignition temperature itself for several mixtures can be evaluated using the set skin approach apparatus, which is the standard test apparatus for this. So, ideally conditions are used to determine the auto ignition temperature of several mixtures.